So it's fantastic to have so many of you with us this afternoon. My name is Liz.
And I'm Charlie.
And we're based in Cambridge as part of the Enrich team. You may have come along to some of our webinars before. And before we get going, I'd just like to say a big thank you to Trinity College here in Cambridge, who fund them for us so that you don't have to pay to come along. So this webinar you may be attending because you've recently become a problem-solving school, or perhaps you're just coming to the end of your first year, but it's part of a series of webinars. We are on webinar number 4 in our current series, and we will show you towards the end of this webinar where you can find the recordings of the previous webinars and the associated guidance that we've written. We'd like you, please, to think about this webinar as part of supporting you in helping your children on their mathematical journey, their problem-solving journey, as they are faced with problems that they've not seen before. So when you meet a new problem, the first thing you might do is to do some exploring and some noticing. So we're imagining that students are given an opportunity to explore and notice. Having done that, maybe they begin to work a little bit more systematically. So that would be sort of our second stage of the problem-solving process. And that systematic working would lead to some conjectures and some generalizations we would anticipate. But what then? That may seem like a good place to stop initially. You know, we've conjectured, we've generalized, we found what we think could apply. Whatever you throw at us, we found perhaps a general rule, a general pattern. However, that's the difficulty then is that perhaps to students this looked like a little bit of magic, and what we want to make sure is that maths is not perceived as magic. We want to offer the reasoning and the understanding. And so that is where representing mathematics comes in. And what we hope to do in our webinar today is to introduce you to a number of different Enrich tasks that you could use in the classroom to give students an experience of a broad range of representations, which we think will be particularly useful for them, mathematically speaking. We've written some guidance which will summarise, we hope, what we will say in this webinar, and we will show you where that can be found, along with a whole range of tasks to support you, but we'll go to that at the end of the webinar. We're going to try and work on some tasks for the rest of this session to illustrate those different ways of representing. Charlie, is there anything you'd like to add before we do some maths?
No, I suppose you and I have often talked about how when we were at school, we were given lots of rules, and luckily for us, we were quite good at memorizing these rules, and so we did well enough. Mm-hmm. But it would have been so much nicer if we'd understood why these rules made sense or where these rules came from.
That's right.
How they'd been developed, and that would have given us a way of picturing and visualizing what was going on and why the rules were appropriate.
Absolutely, absolutely, yeah, thanks. Okay, so if you've been along to our other webinars, you may have experienced that sensation of us wanting to give you some opportunities to join in the mathematics yourself, but we also want to make sure we focus on the particular phase of the problem-solving process that we're talking about. So we're going to try very hard to focus on the visualization and the representation aspect of this problem-solving journey. So if we rush through other parts, please forgive us and do watch the recordings of the other webinars. Right, Charlie, and those of you participating, what I'd like you to do, please, is to think of 3 consecutive numbers. And I'd like you to find the sum of those consecutive numbers. So, Charlie, would you like to just talk through? Oh, yes, let's put the visualizer on. Yeah, sorry.
Right.
I think that's an excellent idea. Let's do that. Okay, there we go. Over to you.
So 3 consecutive numbers.
Consecutive numbers. While Charlie's doing this, those of you participating could have a go with your own set of numbers as well.
Right. I'm going to choose 14 plus 15 plus 16. And what do you want me to do?
Add them together, please.
It's 45.
Okay, thank you very much. Those of you who may have tried this at home, well, I'm assuming you're at home, you may be at school still, wherever you are, those of you who tried it, you'll have chosen your own 3 numbers and you've got a sum. Okay, let's try another example, Charlie. Could you choose 3 different consecutive numbers?
Okay, 3 plus 4 plus 5 is 12.
Okay, nice. 45 and 12. I wonder, those of you participating, could you please pop the sum that you have got in the chat, please? Don't tell us your numbers, just the sum. I'll give you a moment to do that. Thank you. We've got 321. They're coming in thick and fast. 80. Would you mind scribbling a few of these, Charlie? That would be helpful. So 36, 18, 21, 15, 30, 300, 27. Wonderful. 33, I can see. 30, have we got 30? Oh, you've got that one already. Yeah, 18 we've got. Brilliant. Okay, so now, as I say, we're rushing through this aspect. This would be part of your exploring and noticing phase. So Charlie, what do you notice about all these sums?
They're all multiples of 3.
Okay, multiples of 3. Now, in the classroom, what we might do now is we might choose to work a bit more systematically to test out some particular examples. Because we would be in a very big group, it would be a great opportunity to work collaboratively, to share all our findings, perhaps on a board or a working wall. And perhaps, Charlie, at that point, maybe we couldn't find any counterexamples. Maybe it looks like that the sum of 3 consecutive numbers is always a multiple of 3.
Yes, and we might then say to students, okay, what do you think happens when you have 5 consecutive numbers? And they might predict that it's going to be, they're going to add up to a multiple of 5, and they could try it and discover that that is the case.
Right.
And do more conjecturing and more generalizing. 7 consecutive numbers, they would add up to a multiple of 7, 11 consecutive, but none of that would explain why this is happening.
Right.
So they could do a lot of exploring, they could do a lot of convincing themselves, yes, convincing themselves up to a
point,
some degree.
In that we can't find a counterexample.
Yes.
Yeah.
And they would do a lot of conjecturing and generalizing, which is fantastic. But it seems to me that they're missing something if, like you said, it's not magic. There is a reason why this happened.
That's right.
And we want students to appreciate that we should be looking for reasons and explanations.
Right, okay. And so this is the point at which then we might offer, we're going to offer some for you here and now, which we hope would lend themselves to you using it in the classroom. And we've tried to choose some representations this afternoon that we feel are widely applicable, not just to the problems we happen to have chosen. So Charlie, what I'm going to do now, I think, is to go to the website. I'm going to stop sharing the camera because I'd like to show our participants this problem on Enrich. Here we go.
So is it 3 neighbours that you're going to show us?
It is called 3 neighbours. Yeah. Okay. Let me just find the correct page. Here it is. So please don't worry about reading the text because the text just outlines what we've been doing together. But what we have done here on the page on Enrich is offered you some, we've imagined that we've got some students offering some representations and we're inviting, in this case, students to have a look at the representations and unpick them. So first of all, Charlie, let's have a look at Liz's method. Ooh, let me try again. Oh, why is it not working? Hang on. I'm not going to panic yet. There we go. There we go. Okay. Oh, thank you. Zooming in. Brilliant. So just take a moment to look at that image. So I wonder whether you, as participants, could rehearse, you might be able to rehearse in your head a narrative around this image. Let me just give you a moment to have a think about that. I'm hoping you might have seen something very similar to this before. So here what we're doing is we're using the idea of blocks to represent numbers. We are representing our consecutive numbers as blocks, but because they're consecutive, they're differing exactly by one. So we're going up in order of size. These are our three consecutive numbers. And what we're showing is that on the largest of the three, we could take this end block, the one from the end, we can move it to go on to the first of the three, and then we are left with three identically sized blocks, so three identical numbers. And we know, therefore, that because there are three identical numbers, the sum will be a multiple of three. Charlie, I think quite significantly, and perhaps this is the part that that is useful for you to draw students' attention to in particular, these dotted lines here. I wonder if you could tell us a bit about those.
Right. So I suppose if you didn't have a dotted line, so I'm going to think of them as columns rather than blocks.
Yeah, thank you.
The original one might have looked like 3 plus 4 plus 5.
Indeed.
Because the first column has 3 squares and the next one 4 and the next one 5. And so that would be showing me that 3 plus 4 plus 5 is the same as 3 lots of 4.
Right.
But that doesn't seem to be very general. It's just very specific to that one example.
Yeah.
What the dots do for me is to say, well, it doesn't really matter how tall that column is. I would have quite liked to have had a sort of a line at the bottom so that they're all starting from the same base.
Okay.
But I think that's implicit, so I'm not too fussed. But it just shows that we're just looking at the top of the columns. Yeah. The columns could be of any height. So, for example, the one on the left could be 3 plus 4 plus 5 above 100 squares below. So it could be 103 and 104 and 105, and they're going to add up to 3 lots of 104. 3 lots of the middle one.
Absolutely.
So I think the dotted lines adds the generality to what otherwise would be very specific.
Very nice. I like what you said there. Actually, you added the fact that this is 3 times the middle number, which we hadn't mentioned already. And in fact, the question that we're not invited to consider that, but actually this representation makes that very clear as well, doesn't it? It gives us that extra insight.
And because I knew that when you asked me to do the sums, and I had to add 14 and 15 and 16, I trebled the middle number because that was an easier way for me to do
very
the sums.
Efficient, very efficient.
Easy, yeah. Lazy.
Lazy, yeah. So we offer students this representation for them to, as I say, unpick, to get to grips with how the representation helps them understand why 3 consecutive numbers always add to a multiple of 3. Now, did you want to say something? I
think what's also incredibly powerful about this is that I can now imagine what would happen if I had 5 consecutive numbers, and I would take 2 from the far right and put it on the far left. I take 1 from the one on the right, but not the far right, and add it to the second one.
Yeah.
And then I would end up with 5 columns, all of the same height as the middle one. And so I'll have some reason for I can already start anticipating what's going to happen with 5 consecutive numbers because I've got a model for what happens. And I can anticipate what's going to happen with 101 consecutive numbers.
And actually, what's also really nice is the fact that although our representation here we've drawn, or we might create using multi-link. What you're talking about now, Charlie, I mean, obviously you've had lots of experience and students would need to have lots of experience in this, but actually now you're talking about internalizing the image. So your representation now is not on paper anymore, it's internal to you, which means that you can draw on it whenever you need to.
And I'm not memorized. I think
no, that's an interesting important distinction, isn't it?
I've got, this makes sense to me.
Yeah.
I don't, you asked us to look at the image and try to make sense of it.
Yes.
You didn't have to talk. I mean, you know, we ended up talking through our explanation of what was going on for us.
Yeah.
But for many students and for most of the teachers today, they will have made sense of this themselves.
Yeah.
So it's not about having to memorize this image. It's about having an image that makes sense and we can draw from.
Fantastic. Now, if we just scroll down this page, you will see, I just want to very, very briefly mention Claire's method as well. As we get to the top of primary school, we start to think about algebraic representations. Now, obviously, we're encouraging children to think in an algebraic way at a much younger age. But in terms of the algebraic representation itself, we might start to think about that at upper primary. And so, you know, we could express we could explain this result in an algebraic way as well. Now, I think we often perhaps think that as children move up into secondary school, we're encouraging the algebraic representation beyond the visual. However, I think what is really apparent in this problem is that the pictorial, the visual representation offers a much more intuitive way of understanding this situation compared with the algebra, until you become very, very, very fluent with algebraic representations. I don't know whether you'd like to, we've got to go back to cat.
Apologies that there is a cat that's decided that it's going to join us, our mathematical cat.
Is there anything you'd like to add about the algebra there, John?
Yes. Eventually, I do want students to be able to interpret n plus 1, n plus 2 as consecutive number, representing consecutive numbers.
Yeah.
When they add them, they get 3n plus 3. And then at secondary level, when they factorize that, they say, oh, that's 3 lots of n plus 1.
Yeah.
And n plus 1 is that middle column.
That's right.
And so I do want the algebra and the visual representation to be two sides of the same coin. However, I completely agree with you that the image gives you that, I can see why this is happening,
yeah,
in a way that perhaps is not quite so obvious for the algebra. So I do want them to have lots of experience with the visual, and that when they do the algebra, they connect it to the visual.
Absolutely. Thank you,
John. And unfortunately, sometimes the algebra we
don't make those connections.
No.
Yeah. Okay. Brilliant. Okay. So there's a first taster of a task on Enrich that offers students some experience of some different mathematical representations. What we're going to do now is we're going to move on to a different task, and I think I'm going to go back to sharing the paper here that Charlie's got, because I'm going to set Charlie and you at home a new challenge. Actually, do you know, I'm not going to share, I'm just going to show this image quickly first, just to set the task up.
I could copy it here.
Okay, here we have a bag full of ones, a bag full of threes, a bag of fives, and a bag of sevens. You have an unlimited supply of ones, threes, fives, and sevens. And my challenge to you is this. I would like you, please, to choose 5 numbers from those bags, which, when added together, make a total of 20. So 5 numbers from the bags, making a total of 20. So just have a little go to start with, and I'm now going to share the paper that Charlie's got here as we perhaps watch what Charlie has a go at. Here we go, Charlie. There we go. Oh, you're going to have to move it down a bit. If I move this, gosh, this thing is so counterintuitive. There we go. There we go. That's just about okay, I think.
And I need to add five numbers.
5 numbers,
One
please.
plus another number. And 20.
Yes, please. Yeah. So if you find 5 numbers from the bags that add to 20, please do post in the chat. Let's make sure we've got the chat up here so we can see it.
So we want to know which numbers they've chosen.
Please,
they've used.
sorry, I should say that. Yes, please. If you find
and
5 that
we need to use exactly 5 numbers.
Exactly 5.
We can't use.
Thank you.
I think, Jeanette, you've gone
Possibly
to 21.
Slightly over 20. Yeah, possibly. Just to double check. So 5 of these numbers to make a total of 20. That's right, Jeanette. Always good to check. One minute.
It's recording.
Thank you, Jasmine. Oh, I see you haven't written that message to everybody. Jasmine is saying that she had to go at this task with her class. It was good for resilience. Charlie, have you had a go at this? You seem to be leaving it for everybody else to have a go at. I notice you're sitting back.
I noticed that Emily is saying that she thinks it's impossible, and I'm trying to understand why she thinks it's impossible. This is a bit late in the day, Liz, for you to give us an impossible question.
Is it? It's interesting though. But, well, I might argue that's not the case, Charlie. But let's perhaps leave it. Should we get 20 more seconds and then we'll unpick this maybe. Okay, shall we have a little think about this all together? So it's an interesting point. So Emily thinks that, well, and Laura's chipped in as well, that maybe we can't find 5 of these numbers to make 20. Giving students, although you see, although we cannot find an answer, so it is impossible in the sense that there aren't 5 numbers that are going to make 20. I might well have set you a test like that, Charlie, because actually we can still find a solution. We can still reason why. And that's where our representation comes in. How often actually do we give students these kind of opportunities? And this is exactly what mathematicians do. I mean, we are very fortunate. We're based in the mathematics department of the university here in Cambridge. And although I have no idea about the mathematics that the researchers work on, I imagine that they have a question that they're working on, and they're trying to work out, whether what they're investigating could be true, whether it isn't true, whether it's sometimes true, the conditions, and actually giving a question like this to primary age students gives that experience of reasoning why we can't find an answer. So Charlie.
But also, I mean, one way of convincing ourselves that this is impossible is to try all the possible combinations. And that would take a long time.
That would take a long time. We could just about do it, I guess. But
we
yes,
could.
We could.
I think we could try all the possibilities and convince ourselves. But that is very time consuming. So it is quite nice if we can find an elegant shortcut to this.
Yeah,
absolutely. And a visual representation might be the answer in this case.
Might offer.
Given that I've seen some multi-link.
You've seen some multi-link, yeah. Okay, so of course, you know, Emily and Laura, for example, have noticed that all the numbers that we were offered, all the numbers in the bag, were odd numbers. Now, many of you, I am sure, use multi-link, not multi-link, Numicon at school, perhaps, which I think offers a very powerful representation of odd and even numbers. What I've done here is I've just created some multi-link models of odd and even numbers. So without labouring the point, this idea that we've got, you know, pairs. So we've got 3 pairs, 3 lots of 2, and the 1 to make 7.
So are you thinking of it as I have an even number, and then whenever I add 1 to an even number, I make an odd number?
I make an odd number, yeah. Thank you for clarifying. Yeah.
This is even because I can sort of share this evenly between 2 people.
That's right, yeah.
Or fairly evenly, and then that makes it odd.
That makes it odd.
I can't share it evenly anymore.
I can't.
Okay.
I can't. So here I've got, you know, 5 odd numbers. They're not all different, but I've got 5 odd numbers. And so if we're thinking about how we're summing these 5 odd numbers, I guess I can quite nicely pop 2 of them together. And now it's very obvious that I've got an even number.
And if I add another one?
Now we've got an odd number.
And if I add another one?
Now it's even again.
So again, this image, it's useful because it's not just about the one particular case.
That's right.
I can start using this image and imagining 2 odd numbers, 4 odd numbers, 6 odd numbers. So it seems to me that the power of some of the images that we're sharing is that they go beyond the very particular case.
Exactly. Thank you, Charlie.
I see. And you gave us 5 odd numbers.
I did.
Okay. So 2 will make an even, another 2 will make an other even. So yes, so whoever said this was impossible, we're going to get an odd total.
We're going to have an odd total, yeah.
So we're not going to get 20.
We're never going to get 20 with 5 odd numbers.
And we will always get an odd total. So if I come back to this, whichever 5, if I choose 2 1s, a 3, a 5, and a 7, for example, I'm going to get 17. I'm going to get an odd total.
That's right.
Rather than...
That's right.
Oh, thanks for giving us some. Okay.
So you may well have come across that problem like that, or one's very similar to it. Now, on the Enrich site, which I'll just go to now.
Can I just
go on.
So I might, so if I was doing the diagram for this, I might be tempted to do what you did with Liz's approach earlier, where you're doing
the dotted lines.
So that can be, starts there, it can carry on.
We can have any number of pairs in between. Yeah.
And then I'm going to use the orange because, and then I can picture this doing something like this.
Yeah. Any length.
And then I can picture what's going to happen when I join them up. That odd one out and that odd one out will pair up, and I will get an even number of blocks. Yeah. And the dots there reassure me that this is going to happen for any
size,
2 odd numbers.
Odd numbers, exactly. Yeah. Thank you. Brilliant. So that problem on the Enrich side, we simplified it slightly, just so so that you have slightly less arithmetic to do. Let me show you on the site where it is.
And we've linked to all these problems on the guidance.
We'll show you where we've linked to it. So this is the task on the NRICH side. It's called Make 37, and it offers you a fantastic opportunity to really to demonstrate ways of representing odd and even numbers that, as Charlie said, can be applicable to all sorts of situations. Charlie, I think
I've got a question here, which I think could make use of the two images that we've shared so far.
Lovely.
So my request to everybody is to choose 4 consecutive numbers and add them up and share in the chat what your total is.
Okay.
And I'll do the same
drawing
on my...
Yep.
So I'm going to choose 7 plus 8 plus 9 plus 10. Gee, I've made that difficult for myself.
Okay. Shall I read out a few numbers we've had so far?
Yes.
So these are the total. We've got 42, 50, 86, 38. Yes, 10, you're right. 30. 46.
2. So it might be easy to describe them all as even numbers.
That leaps out at us, doesn't it?
Yes.
Well, it certainly leaps out at me. And when you say it might be easy, you're suggesting, Charlie, that there's more to it?
Well, I just haven't found any multiples of 4 in this list.
Oh, that's interesting.
So has anyone managed to add 4 consecutive numbers and get an even number, which is a multiple of 4?
Okay.
Because this is 2 more than 8, 2 more than 40,
Yep.
2 less than 52. 2 more. These all seem to be either 2 more or 2 less.
I agree.
Than or 2 more and 2 less than multiples of 4. Has anyone found 4 consecutive numbers?
Doesn't look like it so far.
So I think we can explain what's happening using the 2 images that we've offered so far. I'm going to do this quite quickly because I know we've got other questions we want to do.
Okay.
So your 4 consecutive numbers could have started even, odd,
Yeah.
depending on whether you started with an even number or not, but you might have started with an odd number.
Yeah.
And then the next one would have been even, and the next one odd, and the next one even.
Yeah.
And because we know that 2 odds, so you would always have got 2 evens and 2 odds.
Yeah.
And we know that 2 odds add up to an even.
Which we demonstrated earlier, yeah.
We did earlier with a multilink.
Yeah.
And we know that evens plus evens make more evens, and I can picture that.
Yeah.
So the total, when we add them, is going to be even. And likewise here.
Yes.
We've got the odds. The 2 odds will add up to an even.
Yeah.
Add another even, add another even.
So that leapt out to us, didn't it?
So that explains why I was always getting an even total.
Yeah.
But it doesn't explain why we didn't get multiples of 4.
It doesn't explain, no.
So I think I'm going to use your method from Three Neighbours.
Yes.
But this time I'm going to put a base on my columns.
Good.
So, I've got my dots. I'm going to start again. Thank you. So I got my dots. So I'm going to start my 4 columns.
Yeah.
And I'm going to then have 4 columns which go up by 1 because they're going to be consecutive numbers.
Yeah.
Gee, my columns are a bit wobbly.
We'll let you off that. We'll let you off.
Okay.
Good. Mm-hmm.
And I'm going to take the top square off that one.
Yeah.
And put it here.
Okay. Yes.
And I'm then going to say, I'm going to imagine this part of the column. So this,
yeah,
and this, and this, and this are 4 columns of identical height.
Yeah.
So that bit must add up to a multiple of 4.
Yes.
But I've still got 2 blocks left over.
Nice.
So I've got a multiple of 4, which I know is even.
Yes.
Plus another 2.
So I know it's even, but it's not a multiple of 4.
It's 2 more than a multiple of 4.
Nice.
And that is why all these numbers are even, but not, and all 2 more than multiples of 4.
Yeah.
So we're using the 2 images.
Yeah, nice.
Yeah.
Combined. Fantastic. So powerful. So powerful. All right. Let's try another task now. Charlie, I'm going to leave the paper there. This is one for everybody to have a little go at the same time. So I'm going to ask you to do a calculation in your head, and I would like you to then just think about how you did it. Okay, so Charlie, so the calculation is 18 times 5. So please, if everybody think, what is 18 times 5? How did I work that out? Okay, hopefully you've had enough time to find an answer and then just sort of unpick how you did it. Sometimes we do these things automatically, don't we, without really thinking about it. So Charlie, how did you do it?
I thought of 20 lots of 5.
Okay.
Because I can do that by thinking of 5 20s.
Yeah.
I know that 20 times 5 is the same as 5 20s. Because I've got a picture of a rectangle with dots or crosses, an array.
Yeah.
And I can either have 20 rows with 5 dots on each.
Yes.
Or 20, or that's also the equivalent of 5 columns with 20 dots in each.
Nice.
So depending on what, I can think of it as 20 rows of 5 or 5 rows of 20, depending on, And so I can have 25s, which I know is 100.
Yes.
But that's too many, but I only wanted 18 5s. So I'm going to take away 2 5s. So I'm going to take away 10.
Nice.
And I'm going to get 90.
Fantastic. Thank you. Okay, so Charlie, so I have got a little representation of that, I think, here. So I think what you've done is you've thought of your array of 20 by 5 or 5 by 20, and then you've done 2 lots of 5 too many, so you've chopped off 2 lots of 5, so you know you're left with 18 times 5.
Okay.
Thank you.
But I could have done it differently. I've just realised.
Go on then. I can see people are contributing on the chat.
Okay.
I won't tell you. Okay. Okay, yeah, go on. Give me another method.
Okay, so I might have thought, well, I'm not very good at my 18 times table.
Yeah, understandably.
But I do know that 9 is half of 18. Yes. So if I have 9 5s and another 9 5s, I will have 18 5s.
In total, you have 18.
So 9 5s I know is 45. Yeah. And I got to add the same again.
Yep.
And I get 90 that way.
That's encouraging that you get the same result. And I think I have a representation for that as well, Charlie. So here we've got our 18 by 5 array, our 18 by 5 rectangle, and we've just chopped this into 2 smaller rectangles, which I'm sorry, my scale is not very good. They look rather square, don't they? 2 lots of 5 9s. Okay. Any other ways of thinking about it, Charlie? Or we could look at
I suppose when I'm doing very big numbers, so
Mhm.
18 fives, I might have said, well, I know what 10 fives are,
Yeah.
and then I need to add 8 fives.
Right. So what you're doing there, you're decomposing 18, I guess, aren't you? You're
Yeah.
splitting 18 in a different way.
So
Okay.
10 fives are 50,
Yep.
8 fives are 40, and I'm getting 90 that way.
Nice. It's a different partitioning. And lo and behold, we've got an image of that, a representation of that as well. Charlie, I'm going to do it slightly the other way around.
Okay.
Can I offer you a, well, let's have a look at this one first. I wonder if you could talk me through, if I have drawn this pictorial representation of my method,
Okay.
could you create the
So
calculation?
this doesn't seem initially such easy, but actually, because we do work on angles, and we know two lots of 180 degrees makes 360.
Maybe we know our two lots of 18.
I can do two 18s as 36.
Yeah.
Two lots of 18 is 36. And then one lot of 18 is 18. Maybe I know that if I go around the circle twice, two lots of 360 is 720. So 36 and 36 is 72.
Yeah.
And another 18. Well, I know it should be 90, so I'm going to assume it is 90. But I get a cheat.
We'll let you off. Now, what about this one? This one I think is perhaps a little bit harder. Do feel free to annotate.
Okay, so that's your 18 times
rectangle.
5.
Yes.
And I think you've cut it in the middle. I'm assuming you've done that, which is sort of 9. So 9 and 9
yes.
and 5. And you're taking this, bringing it here.
Yes. And how does that help?
And that helps because now I've got 9
yes.
by 10. So you've got 90.
Calculation again. Nice.
So that is sort of, okay, so I had 18 fives. And so if I double that, I get 18 tens.
Yes.
Oh, but I've doubled, but I've got to halve that. So I think of 18 tens as the same as 10 18s.
Yeah.
So I'm going to halve that, and I'm going to have
9 tens.
Which is 90.
Which is 90. Brilliant, thank you.
Okay.
So here we've got, we're offering representations which build children's understanding of a numerical method, a calculation method. Now this, you may well have chosen a different method yourself. I wonder whether you could create a pictorial accompaniment for your method.
And what seems really important is, in this case, there may be some more easier than others.
Yes.
But actually having a variety of images means that I could choose between them depending on what my numbers are.
Yes.
And
spot on.
If students are going to be resourceful, they need to have more than just one tool in their kit bag when they come across a problem. Yeah. They need to know that they can sometimes choose one representation, but at other times use a different one because the numbers make it easier. Exactly.
So that particular problem is called Picture Your Method. And if I just show you very quickly on the site, because I know we've got one more task we'd like to share with you, but very quickly, in the task on Enrich, we have got, first you can see some different, some descriptions, students describing how they have come to their solution. And then what we've got are the pictorial representations that I showed you, and students, in the way we've set up this task on Enrich, is the idea is to match the description of the method with the representation. And that's come from an idea from Joe Bowler on YouCubed, as is referenced at the bottom. Charlie, I think we've got one more. So far, what we've done is we've offered some visual representations. Yes. We've touched on some algebraic representation. But I think when we were talking about visualizing and representing, one area that we kept coming to as well was our use of language in mathematics, and how the words that we choose to perhaps describe what we're doing or to help students unpick a method can be key and can really help or potentially hinder. Yes. So we're going to offer you an example of that before we say goodbye. Charlie, I'm going to give you a subtraction calculation. Now it's going to involve three-digit numbers, three-digit whole numbers. So I'm going to suggest you lay it out in a column method. So I'd like you to have a go at 528, take away 365. 528.
I'm going to change it to 523, if that's okay.
You may do that. Yes, okay. I'll let you do that.
Okay.
Yeah.
Is that what you want me to do?
Yes, please.
Okay.
Yes.
We need to share what I'm doing.
Oh, I'm so sorry. Yeah, there we do. Sorry,
you don't mind me changing the numbers?
No, I don't. Back to the visualizer. There we go. Okay. So Charlie, as you're calculating, what I'd really like you to do is just talk through out loud what you're doing, please.
Okay. Well, I'll tell you what I was taught to do.
Do that then.
If you let me put on the spot here. Okay. This is, I think, what I'm just remembering back about 60 years. Okay. 3 take away 5 can't be done.
Right.
So I'm going to borrow 1.
You're going to hang on.
Well, yes, I'm going to borrow 1. And,
what do you mean by borrow? When are you going to give that back again? When we use the word borrow, I think of it as a temporary loan.
Okay, right. So what would you like me to say instead?
Well, I know that those of us watching today will not be surprised to learn that actually the language to use now, if we think about here, we're looking at 3 ones and we're trying to take away 5 ones. So we've got too many to take away. So here we're going to go to the 2 10s. I'm going to take one of those 10s and we're going to exchange the 10.
All right.
So the 110 becomes, we're exchanging it for 10 ones.
Okay.
And so that is what you've done here. You've represented here the 10 ones. So your 10 ones and your 3 ones become 13. So that's what we've got here. So this language, it's something that we can slip into really easily, the borrowing analogy. But actually, mathematically speaking, the language of exchange offers students some insight into the understanding what we're doing. And I remember when I was at school, I had some bizarre way of remembering what to do without any understanding. You touched earlier on the fact that I was lucky I could remember, but I did not have that backup in understanding.
So you want me to talk about, so I've got 13 ones, I can take 5 ones away, and I'll be left with 8.
Yep.
And I want to take 6 10s from 110. I can't do that. So I'm going to look at the hundreds column.
Yep.
I've got 5 hundreds, and I'm going to exchange one of these, leave the other 4 behind, and then exchange that for 10 10s.
Nice.
Now I already have 1 10, so I'm going to have 11 10s altogether.
Nice.
And now I can take 6 from the 11. And I'm going to take 300 from the 400 and I'll have 1.
Brilliant. So it's
an exchange rather than borrow.
Exchange rather than borrow.
And I'm going to make it very clear that I'm exchanging a 10 for 10 ones, or 100 for 10 10s, or 1,000 for 10 hundreds.
And of course, in the classroom, the use of Dean's, for example, Dean's blocks, which I know are used very widely, really helps students to get this idea. But then transferring it to paper, using that vocabulary is really useful.
I've also seen people do this when they do the subtraction.
Go on. Yeah, go on.
Where they say, I've got no idea what they say. I won't say anything.
Okay. Should we watch and see what's going on?
They do this. Well, you can't subtract 5 from 3.
Yeah.
So I can't subtract 7 from 2. 12 take away 7 is 5. 5 take away 4 is 1. So both methods have given me 158.
Right. So what's going on here?
Is that everybody's homework?
It could well be. I think this is intriguing. Until you showed me the other day, I had not seen this before. I think so. Perhaps it's a good idea to let everybody think about it. I might use I might think about how keeping the difference between those two numbers the same. So I'm doing something that keeps the difference the same.
Okay, so two children who are siblings,
Yeah.
whose age is 4 years apart,
Yes.
in 10 years' time, they will still be 4 years
Still be
apart.
4 years apart.
And 10 years later, or 100 years later, they'll still be 4 years apart.
So we've just added the 10 or the 5 on each time to both numbers.
I added 10 ones to the top number,
yeah,
and 1 10 here. I added 10 tens there,
yeah,
which is the same as adding 100 to that.
Right.
So the difference between the top number and the bottom number. And when we're subtracting, we're looking at the difference between two numbers.
Exactly.
We said enough.
So nice.
We need to show people.
We do. We're running very slightly late, but let's go now to the website and let's show you. We hope we've given you a flavour of some useful representations to introduce children to in the classroom. If I go back to the website, let's go, if I go here, I'm going to go right up to the top menu. If you click on our problem solving schools page at the top there, and we're going to go to the right hand box. And here we're going to, if we go all the way to the bottom, this is where you can find the recordings and the guidance that we've already created. On the left-hand side, this left-hand column is linked to guidance, and at the top of each of these pages are the webinar recordings. And the new ones that we've just completed, which we hope we've given you a sense of today, are the visualizing and representing ones. So here you've got a whole collection of tasks which are grouped by year, which we hope you will explore and have a look at with your children to give them a flavour of different representations available to them. And if I go back, let's just quickly show you the guidance. So the way we've structured our guidance is just a little bit of an introduction. We've inviting you to think about the values and ethos in your classroom, which will then influence the way that you introduce these ideas. We've offered you some examples there of tasks that might be particularly useful. You'll find links to all the tasks that we've had a look at today. And we've split it up into those which lend themselves to visual representations, and then some which lend themselves to algebraic representations. And then we've added a separate section which is about that sort of analogous content and the use of language. So where you see subtraction surprise here, that links quite nicely to what we were just doing with our subtraction calculation.
Everyone's going to get an email in tomorrow, the day after, with a link to this page.
Absolutely. And I'm just going to pop in a link now to the evaluation form. We hope you have found this afternoon session useful. Please do give us your feedback, because it does help us to improve. And our
funders are always keen to be reassured that their money is being well spent.
Absolutely, absolutely. We hope to see you again at a future webinar. The fifth and final one in this particular series, so we'll be focusing on reasoning, convincing and proving, is not until January the 21st, the primary one. We do have a webinar before that, which is about supporting problem solving beyond the classroom. So we hope to see you at that as well.
That's going to be in November,
That's November the 20th, I think, yeah.
And you can find that on our events page.
All on the events page, yeah. So thank you. We hope you have a good rest of the day, and we look forward to seeing you again at a future webinar. Thank you very much.